Hi, everyone. Thank you for joining us once again. We are here as part of the NEMO Stormwater Seminar Series, and we are very happy to bring to you our stormwater expert, Dr. Steve Souza, who is the owner of Clean Waters Consulting. He will be sharing a presentation on porous pavement applications for the Barnegat Bay Watershed. Thank you, Steve, for being here.
Thank you, Avery. Thanks for having me, and thanks to everybody that's tuning in today. So yes, we're going to talk about porous pavement applications and their applicability for the Barnegat Bay watershed. You've probably heard us talk about this numerous times before that when we have relatively undeveloped watersheds, the majority of precipitation that does fall is either infiltrated or lost via evapotranspiration. Very little of that ends up getting generated as runoff. But as we start to develop our watersheds, we end up increasing the amount of impervious cover. That in turn results in less of that precipitation making its way back down into the ground. So a significant decrease in the amount of infiltration and a significant increase in the amount of runoff. And neither one of those things is good for Barnegat Bay. Now, some of you may think, well, okay, I need to have really high levels of development to start seeing this, things that you would see typically in more urbanized areas like, say, Tom's River. However, that's not the case. This occurs even with as little as about 15% impervious cover, which is on the same level of development as maybe one house to two houses per acre. So typical suburban development and the type of development that we see quite common throughout the entire Barnegat Bay watershed. So there are various strategies that a lot of you are familiar with in terms of managing runoff. And these best management practices of BMPs can be divided into three different types of categories. We have brace stormwater, which would be the conventional standard technique, the curb and gutter, where we collect it, we detain it, and then we discharge it, but we don't really do much in the way of managing any of that runoff. Then we have green stormwater best management practices, the type of practices that we've been promoting in Barnegat Bay for the past 20, 25 years or so. We're really focusing on collecting runoff and keeping it on site as long as possible, either to infiltrate it, to passively treat it through some type of biological process, or maybe even store it and reuse it in some capacity. That ends up providing us with a really great way of reducing runoff volume, decreasing storm surges and the erosion that's associated with that increased rate of runoff, and also removing pollutants. But there's another category as well, these green-gray stormwater BMPs, which is sort of hybrid. We're incorporating some of both the gray technology as well as the green technology. And porous pavement falls into that category, a green-gray type of stormwater management, best management practice. Now, the thing is with any of these techniques, but particularly as I'll be talking about today with porous pavement, these applications are very scalable. We can use these in a variety of different settings, whether we're talking about retrofits for, like, say, an individual lot, like a driveway, or maybe a parking lot or a boat launch. So let's take a look at porous impermeable pavement. These technologies have been around for a long time. In Europe, they've been utilized for well over 60 years. And here in the US, definitely over the past 30 years or so. And more so, maybe in the past 10 years to 20 years, we're seeing an increase in the use of these types of pavement systems in the more northern portions of the country, New Jersey, New York, Pennsylvania, and New England. There's a variety of different sources of information out there. Within this presentation, I'm providing you with a few. The American Society of Civil Engineers has come out just recently. This document's maybe now about 3 years old, with a manual that deals with all different types of porous pavement, whether it's concrete, asphalt, or pavers. And that's a good starting point for both engineers and for lay people to understand more about what is porous or permeable pavement. And basically what it is the paving material that has the function and structural support that you would associate with conventional pavement, but yet has the ability to infiltrate stormwater runoff. So it's paving material. Let's think of it with pores that actually facilitate that passage of precipitation from the surface into the ground. In many cases, we can end up with a net positive impact when this is done correctly in terms of a reduction in the runoff volume. That in turn reduces the amount of pollutants that are being conveyed. Less volume means less pollutant loading, and that also means less rate, because if we have less volume and it leaves our site more slowly, we've also tamed some of that rate that causes problems with erosion, bank instability, etc. At the same time, with the correct application of porous and permeable pavements, we can still have no loss in the functionality of those paved surfaces or the stability of those paved surfaces. And as I mentioned previously, in Europe, these applications have been implemented for 50, 60 years. There are a variety of different types of permeable pavements. I'm going to talk primarily about 4 different applications: porous concrete, porous asphalt, pervious pavers, and eco pavers. So the difference, and probably a lot of you have seen slides similar to this, but the difference between conventional and permeable paved surfaces lies mostly with what happens during a rainfall event. On the left-hand side, with conventional pavement, you end up generating more runoff. That runoff leaves our sites faster. There's more contaminants that are mobilized and transported, and there's less opportunity for any of that runoff to get soaked back down into the ground. On the right-hand side of the slide, you can see this is a portion of a parking lot that has been paved with porous asphalt. You don't have any of that standing water up on the surface. As a result of that, we have less runoff, because some of that precipitation is soaking down through that pavement. We are generating runoff at a slower rate. We're increasing the amount of infiltration, so that means we have more chance for recharging the superficial aquifer. And the combination of all of that results in less contaminants being mobilized or transported off-site into Barnegat Bay. Permeable surfaces or porous pavement surfaces, they can be constructed either with an underdrain or without an underdrain. If I have a shallow depth to bedrock or shallow depth to groundwater, less than 2 feet, I'm going to want to construct with an underdrain. And that underdrain does facilitate how that porous pavement operates, but it doesn't take away substantially from its overall functionality with respect to reducing volume, rate, or pollutant removal, because typically you would end up taking the precipitation that is collected by that underdrain and shunt it into maybe a small rain garden or some other type of treatment area. If I have proper conditions, I can build my porous pavement site without any type of underdrain. So I'd have ample distance, at least 2 feet from bedrock or from the high water table. And as a result of that, all of that precipitation that passes through the porous pavement and then down into the ground is part of what ends up recharging the superficial aquifer. As I mentioned, we can do this in very urbanized areas, even areas where I have shallow depth to bedrock or groundwater, by using a combination of my porous pavement with an underdrain and then routing that collected runoff that is intercepted by the underdrain into some type of biodetention area, whether it's a small rain garden or some other type of vegetated basin. Now, one thing to keep in mind is that all of these techniques, with the exception of the eco pavers, all have shared construction and installation attributes, whether we're talking about porous asphalt or porous concrete or the permeable pavers. Essentially, you have your surface, which would be the asphalt, concrete, or paver, that sits over what's called a choker course. This provides stability to that upper surface, and then a reservoir course that provides the voids within which water can collect and be trapped. Think of it almost like as a underground detention basin. And from there, that water slowly then filters through that reservoir course into my natural native soils, or is collected by it on the drain and then shunted to some type of biotreatment area. And in terms of the thickness of that surface, again, whether we're talking about porous asphalt or porous concrete, the material itself is not that different, and neither is the upper layer. It's really the thickness of the choker layer and the reservoir layer that will increase as I increase the intensity of use. So as I go from perhaps, a parking area that is only servicing, cars, no trucks, to perhaps like a residential street, or even a cartway over which heavy trucks are going over on a regular basis. All that really changes is not so much the surface layer, but the subsurface layers. So there's a commonality with respect to construction and application. At the end of the day, what we're really trying to do, and that benefits directly Barnegat Bay, is reduce the amount of runoff that we're generating. Less runoff, as I mentioned before, reduces flooding, pollutant loading, and also that can also decrease if I need to perhaps implement this as part of a restoration or a retrofit type of application. Actually downsize the ancillary BMPs that will be operating in concert with that porous pavement. I can also decrease that heat island effect, because as that precipitation really kind of filters down through that upper layer and then gets contained and held for a while in that those subsurface layers, that helps dissipate heat. So you have less of that urban heat island effect. It's been shown in a lot of these applications in colder weather environments. You end up with less development of black ice or ice in general. So you have less slip, trip type of accidents. So you have a safer surface. And as I mentioned previously, it can be scaled for a variety of different projects, whether it's heavy truck utilization or just nominal use, like say in my driveway. Some of these applications do involve the use of recycled materials, and there's definitely a lot of data now that shows that the service life is very similar to conventional pavement. Those of you that need LEED credits, porous and permeable pavements do provide value in terms of achieving LEED accreditation. And as I mentioned previously, this can be done both in cold weather climates as well as warm weather climates. And these can be just as attractive as standard paving. Some of the cons, though, and where we see pushback, is a lot of times there is this lack of public acceptance. This has to do more with, I think, some preconceived notions that these materials are not as stable, or they're going to break down more quickly. There's also the fact that, yes, initial installation may be a little bit more expensive than conventional surfaces. They do need special maintenance to prevent clogging. That is something that does add a little bit to the long-term cost of these systems. And in high traffic areas, you may find that you don't get that longevity of a conventional surface. However, with some of the improvements that have been made over the past decade, we're seeing that the longevity is about the same, both in terms of porous pavement relative to conventional surfaces. And then, as I mentioned before, I mean, the application of these techniques may not be suitable if I have a very high water table. or if I have soils that are very subject to shrink, swell, or frost heave conditions. And that's typically indicative of soils that are associated with a very high water table. There definitely needs to be, when we use these techniques, particularly the porous pavement, the asphalt, and the concrete, these need to be installed by experienced contractors. And what I've seen also is that because of concerns about the longevity of these surfaces and public acceptance, oftentimes municipal engineers or planning board engineers are leery about using permeable or porous pavement surfaces. There are water quality benefits. This is a table that is from the National Asphalt Pavement Association. So this is not coming from like some, Enviro group. This is coming from the National Asphalt Pavement Association, and basically showing that, yes, porous pavement does have the ability, much more so than conventional paving, to remove pollutants as well as infiltrate a lot of that precipitation. Comparative costs right now, this is based on 2019 to 2021 data. The material cost for permeable pavement is about 10 to 20%, a little bit more than conventional surfaces. Some of that has to do with transport. There are not as many sources for this material, so that adds to the cost. The base excavation and preparation costs, though, are very similar. And in some cases could be even less than for permeable pavement compared to conventional pavement. So the offset that I see, and I've seen in applications, particularly an example we'll talk about a little bit later, is that because I'm increasing the amount of precipitation I'm infiltrating into the ground, I'm generating less runoff. So I need a smaller ancillary detention basin or other type of BMP to help manage that runoff. Now, granted, the maintenance costs, as I said before, tend to be a little bit greater for permeable pavement because they do have to be inspected and swept on a regular basis. But accounting for all those added stormwater management costs, permeable pavements tend to be more economical over a 20 to 30-year life cycle than conventional pavement. And that was all, that information is from a recent report, 2018, that you can check out for yourselves. So let's talk about the different types of porous and permeable pavements, and then we'll get into an example of application within the Barnegat Bay watershed. So we'll start off with porous asphalt. This type of surface has been around for a really long time, probably the most widely used type of porous surface. One thing I want you to notice here is that this particular report done in 2009 is from the University of New Hampshire. So we have a cold weather environment where porous asphalt has been tested and proven to work very well. There are a variety of specifications for porous asphalt applications, depending on whether it's being used for roadways, driveways, or for parking lots. These are just three different sources for those specifications. Permeable concrete, again, widely used, I would say probably more so on walkways, small scale parking areas, things along those lines. Essentially, this is high porosity concrete. It does allow for that passage rainfall into the subsoils. The difference here, and you can see this in in these two pictures at the bottom of the slide, that the permeable concrete has a little more of a rough surface than standard concrete, and that's where you may get some public acceptance pushback, because it's a little bit of a rougher surface and it doesn't look perhaps as refined. However, it does have its place in development and redevelopment applications. Again, similar to the porous asphalt, there are a variety of sources of specifications. Again, this is just a couple of examples, but US DOT, New Jersey DEP, they do provide specifications not only for the material itself, but how to install and maintain those surfaces. And then we have permeable pavers. A lot of you are very familiar with permeable pavers. We've seen a variety of applications, whether it's on walkways, sidewalks, etc., patios. And in this application, even being used in a large parking lot. As I mentioned, a variety of applications. These can be in a lot of situations. You may have some grass that is growing between the pavers, or between the pavers, it's filled with some type of additional aggregate. Typically, they are cheaper than standard concrete, but because of the type of application, costs, and labor associated with it, their use may be a little bit higher than, their installation costs may be a little bit higher than standard concrete. They tend to be more expensive, though, than macadam. However, they do have their place, particularly, I feel like, in patios, parking lots, public areas, as opposed doing this as opposed to conventional concrete or macadam. So I'm going to share with you a case study. This is a project that was done at the Toms River Board of Education for the American Little Society. Funding for this project was provided through New Jersey DEP's 319H funding program. The scope of the project was to basically demonstrate the benefits of porous pavement. And this is a relatively small scale project, but was being done on a demonstration basis. And here we had the opportunity to remove 8 conventional macadam parking areas and replace that with a porous concrete. The cost of this project was about $20,000, not extremely expensive, and that included the removal and disposal of the macadam. Post-installation infiltration rates, we were getting greater than 10 inches per hour, which is about equivalent to the 500-year event. What does that mean? That means I could have this massive storm event, and it would be generating no runoff at all. All of that was passing right through that porous concrete surface. This is the site, and those are the 8 parking stalls that were modified. We also constructed a small ancillary rain garden to treat any excess runoff. This ended up being sort of like a belted suspender application, and in this case, wasn't really needed once we did the post-application testing of the new surface. So we start off with the removal of the macadam, and then the preparation of the base. When we're doing this, a big portion of the work that is being done on retrofit type of applications is to loosen up all of that previously compacted soils. We want those native soils, in this case, that had, very high in sand content. About naturally, we're getting, over 10 inches per hour of infiltration. We wanted to loosen all that back up and return it to as close as possible its natural condition, both in terms of porosity as well as bulk density content. Once we had the base prepared, we came in and put that choker base and reservoir base over the bottom of our native soils, again, being very careful to not compact those native soils. In this case, as I mentioned, because this is being done on a demonstration basis, we did create a overflow underdrain system, but as I'll show you, that wasn't really necessary in this, in this situation. But it was included as part of the overall project. Once we had our, you can see our reservoir base, which is the larger aggregate. We put on top of that our choker base, and then started to lay over that completed sub base our porous concrete surface. So here's the material being laid out. Once it's in place, it's covered and allowed to cure for roughly about 72 hours or so, depending on temperature. You can see here in this particular picture, this is our small rain garden. This is the overflow infiltration under drain, and then that would direct any overflow from these parking stalls into that small rain garden. Close-up of the porous material once it was in place and fully cured. You can see it has a much rougher appearance than standard concrete. After it was set up and cured, we actually came in, put stop blocks, and you can stripe this as you would with conventional pavement. So again, here's our porous surface. Here's our ancillary overflow collection and under drain system. And then here's the little rain garden. This picture I took about 2 months after installation. One thing that you should be able to see right here on this slide is all of this material here. This is just leaf litter and fine sediment that has been washed off of the macadam roadway in the remainder of the parking lot, and that is washed onto our pervious concrete area. And you can see here what's essentially happens is that during storms, although we're mobilizing some of that material from this standard pavement, once it enters our porous pavement area, water infiltrates, and here's where it's sort of everything terminates. That rack line is an evidence of water not flowing over the entire surface of the porous pavement and into that under drain. And as I said before, we did post-application testing and showed that it could convey the full volume runoff from the 500-year storm. The pollutant loading associated with this particular application, we were able to decrease our total suspended solid load by about 95%, decrease our nutrient load in terms of phosphorus by about 80%, as well as decrease our nitrogen load by 80%. And anything that we can do to reduce nitrogen loading to Barnegat Bay is extremely important. Most conventional BMPs only can achieve about 30 to 40% reduction. But once we end up being able to collect runoff and channel that runoff back down into the soils and let those native soils, do what they do naturally, then we can result in very high removal rates for total nitrogen. The maintenance, as I mentioned before, is a little bit more involved than it is with conventional pavement. It does need to be inspected, should on a monthly basis to ensure that there is no standing water, which would be evidence of compaction, and to remove any accumulated debris, and also look for any type of physical damage. The primary thing, though, is that there's no need to apply sand or grit or anything like that for ice control because we're not collecting water on the surface. It flows right through those surfaces. So as I mentioned before, no black ice, less slip and trip type of issues. We definitely don't want to be applying salts because that can have an impact on the stability and actually the continuity of that material. And we definitely need to make sure that our crews are trained properly to avoid damaging, say by snow plows, when, during the winter removing, snow. If in some of these areas where I might have some ongoing development, it's a good idea to remove any kind of tracked mud. We don't want those fine silts to start clogging up that surface. And obviously, we don't want to be applying any type of seal coat to the surface of those materials. In addition to that, if you're going to stripe, as we did with the Toms River application, make sure you use specialized paints that are designed to be used with a porous surface. The basic maintenance requirements, DEP has outlined this in the Best Management Practices Manual, but it involves biannual inspection of the surface for cracking, subsidence, spalling, deterioration, or any type of erosion. So, monthly you should be taking, a quick ancillary inspection, but on a biannual basis, do a deep dive inspection of those surfaces. What we want to do if we start to see any type of vegetation growing on those surfaces, and this typically is something more of a problem or more likely with the pervious pavers, that should be removed immediately. The surfaces do need to be vacuum swept 4 times a year, and they can be power washed. If you're doing power wash, you want to be using a power wash system that has less than 500 psi, and try to avoid doing any type of direct spray on the surface of the material. You don't want to be sort of like pushing fines down into the surface that would add to the clogging. Some of the permeable pavers, they do have specific manufacturers' requirements for their care and maintenance, and particularly with respect to addressing vegetative growth within those pore spaces. So this is just an example of a typical combination sweeper with a low pressure, some type of low pressure application to avoid the clogging of those surfaces. There's a lot of guidance out there. DEP provides specific guidance within the BMP manual, but also, as I mentioned previously, there's maintenance documents out there that provided through the American Society of Civil Engineers, as well as other sources of information, for example, University of New Hampshire. So in summary, these porous pavement surfaces are alternative to paved surfaces. That's a big part of our stormwater strategy for Barnegat Bay. We can significantly reduce runoff volume. When we reduce volume, we reduce flooding, we reduce pollutant mobilization and transport, and that also puts some of that precipitation back down into the ground, which is critical for the maintenance of base flow. There's a variety of different applications, whether we're talking about porous asphalt or porous concrete. And as I've shown in this presentation, this can even be used on high intensity use roadways. Because of some of the specialized maintenance, you do have to make sure that your staff is properly trained and they're aware of where these types of surfaces have been implemented. So with that, I thank you. And Avery, again, thanks for having me. And again, these are applications that I think are very relevant for the Barnegat Bay watershed that can be utilized both new development, redevelopment, and even on somebody's individual property where they want to reduce the amount of runoff that they're generating from their driveway, parking area, or even their walkways. So again, thank you so much for having me.
Thank you, Steve. And for our viewers out there, hopefully this information kind of segues nicely from some of the stuff Dr. Abrupta has been talking about in the greater context of green infrastructure and how we can implement it in meaningful ways in our community. So thank you again, everyone, for being here. Thank you, Steve, for this enlightening presentation, and be sure to check out our other videos as part of this series.